consider coherent. So if two lines that have the same periodicity, they are coherent. We're going to play a game today. So consider lemon a photon. So I give this to you, and I give this to you, you pass it on to the next person behind you, okay? So you can pass it on to the next one, at any rate you want to. Okay, it seems silly now, but it will make sense later. Okay, so are these two lines coherent? No, they are not coherent. They don't have the same periodicity, right? So now I give this two to you, and you only pass it on one clock, okay? So go. Go, keep going. So are these two coherent now? It's not it's because my clubbing is not perfect periodic. But if my clubbing is completely, periodic, they should be coherent, right? They have the same periodicity. So now can one signal be coherent to itself? Any guesses? So the coherent light here. So for yourself, if the early part of the light propagation has the same periodicity as the later part of the propagation, it is coherent to itself. Okay. So what is partial coherence? So now you pass it on to the next one clock. Okay. And then you go without any clocking. So at the beginning there's periodicity, but later on it kind of lost the periodicity. So this is called partial coherence. So now I'm going to revisit some of the concepts we have learned before. So I'm going to, so first of all, if I throw, so we are going to mimic reflection first. So if I throw this to you, reflection, you throw this to someone in front of you towards that angle, okay? Okay, go. Someone please catch it. Okay. That's fine. And can you do a transmission for me? So I throw this to you and you throw it to someone behind you, okay? Anyone? Okay, give it back to me. So now, what is critical angle? So if I throw this to someone, can you mimic critical angle for me? Can I throw it to you? Okay, what do you do? Yeah, So critical angle, that's very good, because in the past sometimes students mimic critical angle by, in the fiber, what we want is light propagate down the core, just like you shoot a bullet into the fiber and it just go down the core. But it doesn't work like that. In the fiber, it's a lot of internal reflections. It propagates in a zigzag pattern. It doesn't just go down, in a straight line. So if you think about the direction that I throw the photon to you, that is a ray model. And if I can afford more lemons, I keep throwing this to you. This would mimic a wave propagation. And so each one of them is a photon. So that's photon theory of light. So let's learn another concept, which is intelligent surface. So it's briefly studied a little bit here. So the surface can be intelligent. It can configure, like the direction of propagation. So I throw this to random people, and then I tell you the criteria. So maybe I throw this to someone, and you forward it to someone who hasn't touched a lemon before. Okay, it doesn't have to be correct, but anyone, go quickly. It's okay. Okay. So how can surface be intelligent? So if there's an intelligent surface in the middle there, and I set the criteria, you forward the signal to a dark zone. So a zone that doesn't have light, then the surface can make a local decision for me. The surface doesn't have to check every decision with me anymore, but I make the criteria, I program the algorithm, so it can make, a localized decision. So, we're going to do a quiz. So one last game, okay? So I throw this to random people. They tell me true or false. So we have 5 statements there. You can just tell me, if you don't know the answer, just take a random guess. Okay? So first one, the EM wave model describes that light propagates in 2 domains and 2 fields. True or false? True. If you think it's true, okay. True or false? Okay. True or false? True or false? Probably true. Yeah, it is true. Why is true?
It's got the electric field component and the magnetic field component, and they're perpendicular to each other.
And then that's 2 fields, right?
Yeah.
Electric field, magnetic field. What are the 2 domains?
I'd assume that's the
Same thing.
perpendicular axes, but I'm not 100% sure.
Okay, so anyone remember what are the 2 domains?
Time.
Yeah, time and distance. So wave propagates over time and over distance. Second, fiber is made by glass. That's the same as window glass. True or false? False. True or false?
False.
True or false? True. Okay. So this is a tricky question. So I said glass is made by fiber, but glass in fiber is slightly different from window glass, because when we manufactured glass in fiber, we increase the temperature to melt it, and when we drop down the temperature, there's no clear transition from liquid to solid. That's why fiber can bend, but you cannot bend this; it will break, right? So that's slightly different. Third one, light waves that are not polarized in the same direction, they don't interfere. True or false? True or false? So, why is false? So, for 2 signals to interfere, there are 2 preconditions. Anyone remember? What are the 2 preconditions for 2 signals to interfere?
Coherent.
Yeah, coherent, very good. And they need to be aligned in polarization, right? So if their polarization, they are perpendicular to each other, they wouldn't interfere. But if there is like an angle between them that's not 90 degrees, then the projection of the first one will interfere with the second one. So here, this is not strict. So in coherent light, do not interfere. This statement is not strictly true, because the perpendicular ones, they wouldn't interfere. Okay? Last one, interference is a negative effect because power can be lost. Who hasn't catched one? Especially for destructive interference. Is that true or false? False. Okay. True or false?
False.
Okay. True or false? False. Okay. Why is false?
The reason that we need to require zero power.
So destructive interference causes zero power. Is that what you're saying?
Yeah.
Okay. So we don't have zero power. Is it a bad thing?
It's
So here the statement is interference is a negative effect, and zero power is a bad thing. but it's not strictly true, because in physics, interference is a neutral term. It's never good or bad. It just means when power is lost here, it will go just somewhere else. But in wireless communications, we often think interference is bad because the computing power of a mobile phone is not really strong enough. You remember you did decorrelating operation to try to cancel the interference. But by doing that linear operation, decorrelating operation, so first of all, you need to do matrix inverse. That's really computational complex. And secondly, you can amplify the noise. So the optimum way is to make a joint decision of all the signals. So when you receive signal, you know they interfere. You make a joint decision over all of them without matrix inverse. But that would give you, so for example, if you have QPSK, you have 4 possibilities. And if you have 2 users, you would have 4 squared total number of possibilities for these 2 signals if you want to recover them jointly. And if you have a lot of interfering sources, this complexity would increase exponentially. That's why you need decorrelating operation to try to separate them. But when you separate them, you also did some harm. You amplify the noise, right? So, but ideally, if you can afford this complexity, interference is not a negative thing, it's neutral. So when sometimes power can be higher, sometimes power can be lower, it's not a bad thing. And whether it's higher or lower, it always tell you something, always tell you some information. And if you can make a joint decision on all the signals, then interference is just there, it's not negative, okay? Okay, very good, that's all for today. See you on Thursday.